So this is my STARS presentation. My lab was, my principal investigator who headed the lab was Dr. Jim Jang, and the department he was in was developmental biology. So basically what I got to work with during the summer was cancer biology. And my mentor was Chin Si, and she was a postdoctoral fellow. So the background of my project is about kinases, which are proteins that are heavily involved in maintaining cell homeostasis and regenerating cells. So they're involved in mitosis, the process of cell division, and also RNAi, which for those of you that don't remember is RNAi or RNA interference, which basically goes through a process to block a specific protein so that that protein or actually anything in the cell doesn't get its job done. So my goal was to identify new protein kinases that are involved in maintaining homeostasis in the Drosophila midgut, which is the fruit fly's intestine. And as you can see through the picture, that the fly's intestine is pretty similar to our intestine, so that's why we use the fly. It's relatively easy to work with in short lifespan, made it easy to work with. And so the long-term goal for this project was to find potential drug targets, because if stem cells get out of control, then tumors form and cancer occurs. So we wanted to find cancer drugs. The method was we would obtain flies from Vienna and Bloomington crossed with escargot for UAS-GFP, which is just a long name for the type of fly that we had. And the UAS-GFP was really important in my project because that was the method that the fly cells had green fluorescent protein, which means that when they divide, they shine green under a microscope, so we'd be able to track the level of differentiation and proliferation in the fly, so how many stem cells were actively being used. So what we would do was treat them with 3 different types of quote-unquote medicine: sucrose, which was the control treatment, and then ESS and bleomycin. And what those 2 drugs, ESS and bleomycin, would do would be to cause the intestine to have a little tear in it, so that we can see how stem cells in the intestine would react and how they would fix that problem and whether or not they would form tumors. So the way we would do that was GFP and pH3 levels, and GFP is green fluorescent protein, as I said. And pH3, we'll talk about that in later slides, but it's just another way to measure the type, the amount of proliferation. So this is the specific type of fly I worked with, and as you can see at 29 degrees, the cells turn green when they're actively proliferating. And so the ISC and the EE are the parent cells, and then the EC and the EE are basically daughter cells, and that allowed us to see how many cells were, again, dividing so that the tear would be. Alright, so just overall results, and then I'll go into the specifics. We tested 8 kinase RNAi lines and found that 19 had an increase in proliferation after they were knocked down, which means that the RNAi would work to cancel out the kinase, and after that kinase was knocked down, then we would be able to see how the intestine reacted to it. So those 19, after the kinases had been knocked down, led to a decrease in proliferation, whereas the other 8 led to a decrease in regeneration after drug treatment, which means that normally they would promote proliferation. So to get to the pictures, on the right or on the left, you see the GFP, which shows the amount of cells that are dividing by green. So the lower 3 PIK kinase and the 2 OPK kinase 10 or 1 and 10 both had an increased level of proliferation because the whole count was green, whereas the control group didn't have very many cells dividing. So these 3 are examples of cells that restrict, of kinases that restrict intestinal stem cell growth, because as you can see, when they were knocked down using RNAi, the green in the intestine dramatically increased, which means that there were more stem cells. And the pH3 is just another level of measuring it. You can't really see it because the resolution isn't very good. these were part of the 8 that led to a decrease in regeneration after they had been knocked down, which means normally that they promote proliferation, so they want stem cell, they promote stem cell growth. So as you can see, when, for example, histone serine kinase was knocked down, there was little to no green in the intestine, whereas the control group was basically covered in green. So that means had histone serine kinase been working regularly, the intestine would look a lot more like the control group, it would be covered in green, meaning that that specific kinase is needed to promote stem cell proliferation. So that was the DSS treatment, which was one of the drugs we used, the bleomycin treatment. Had the exact same results, which showed that those 3 kinases are definitely necessary to promote stem cell growth. Again, the histone serine kinase, for example, had little to no green in the gut, which means that normally, if it had been functioning regularly, it would look a lot more like the control group, meaning that it's necessary for stem cell. So this is the pH3 number, and like the previous slides, it shows that the control group very extremely differently from the specific kinases. So, for example, the ones on the left normally restrict intestinal stem cell growth, and the ones on the right usually promote it as, like, they should look a lot more like the control group than like the high bars or the low bars. So our conclusion overall, we screened 80 different kinase RNAi lines and found that 19 are needed to restrict intestinal stem cell growth and 8 are needed to promote it. And by checking other projects and using our own results, we found that kinases are also involved in things to maintain homeostasis like unfolded protein responses, cell cycle controls, and cytoskeleton organization, which basically keep the cell intact and allow it to divide properly. So future directions, this is what my lab's going to do without me. They're going to obtain more stocks from different resources just to confirm my resources. And then they're going to go in deeper and specify the cell type that contributes to each phenotype, meaning where along the path is it the parent cells or the daughter cells that the kinase is specifically targeted. And then once they figure out that, they'll go in and identify the direct target within each cell of the kinases. So where exactly the kinase targets per cell so that it either increases stem cell growth or restricts it. Alright, so my experience, the program was great and it was a once in a lifetime opportunity. Like, I would have never gotten a chance to learn this in chemistry or biology at Jesuit. So the top 3 pictures are pictures of my lab. The one on the left is examples of the fruit flies I had to dissect. The one in the middle is their guts, or their intestines, which you can't really see, but they're pretty small. And then the one on the right is my workstation. And then, other than the research aspect of this program, Dr. Rabin and Ms. Tam also wanted us to meet new people. So we got to go to seminars with other heads of labs to learn more about their projects. We had the one in the middle is right before scavenging hunts that we had around campus. So that was the day that we got to run around and explore the campus, look for specific things. And then the one on the right is just a picture that, on 7-Eleven day we went to 7-Eleven and got Slurpees. So, it was also my acknowledgements. Any questions?
Trevor, this is more about your experience in the program. How did you feel doing this in high school has helped you direct what you want to do in science? Because I know you want to study science and there's a way you kind of explore explored and done in high school, but how has this kind of shaped or fine-tuned a little bit this experience?
Like I said earlier, it gave me an experience that I normally wouldn't get in a classroom. So that's one of the main reasons that I would have, that I like to do this program. And before this program, I was really struggling between whether I wanted to do more like medicine-oriented science or research in the lab. And this program definitely gave me greater appreciation for the research because I hadn't really previously thought about the time and effort that researchers take to, I guess, for example, make the medicines that are used in clinical science.
So, can you describe the process of dissecting a fly? Because they're so small and it seems really ridiculous.
Yeah, that was, I think, the worst part of my experience because my mentor wanted me to dissect 30 flies in an hour, and I actually wrote my college essay on that. That was like a large obstacle that I had to overcome because, yeah, like the first 2 weeks I couldn't even dissect one fly properly, and by the end I ended up helping other like postdoc pro fellows who had been there for like 10 years, for example, with their fly dissections. I mean, it took a long time and a lot of overtime, and I tried a lot of various techniques to do it overall. Science joke of the day, right? Dr. Rabbit wants me to tell one. This is the one I said in my interview. What do you do with a dead chemist?